Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Welcome back. We're going to go ahead and dive into derivatives of the inverse trigonometric functions here. And when we do this, we are going to take a very theoretical approach by proving some of these first. Maybe I'll just prove one, maybe two of them, because your instructor should have you prove quite a few of these if they can on the homework or something like that. So the derivatives of the inverse trigonometric functions, before I dive into them, I just want to tell you, these are so important. I kid you not. When you go into Calc 2, you'll need to know this stuff just like you know the derivative of x. You have to know what the derivative of sine inverse is and derivative of tangent inverse. Those two are the most common. So these two that I've highlighted are critically important in Calculus 2. It doesn't really help you to remember that the derivative of the cosine is negative 1 over the square root of 1 minus x squared. It's the opposite, actually, of the sine inverse, right? The derivative of the sine inverse. And actually, the derivative of the cotangent inverse is kind of worthless to remember because it's just the opposite of the derivative of the tangent inverse. The other two, the cosecant and secant inverses, I don't have very many students that actually memorize those. And I don't really think there's a super duper need to memorize those. You do encounter them, don't get me wrong, in Calc 2, but generally speaking, by that time you have so many other things on your plate, you don't really remember this formula for the secant and the cosecant, so don't really worry about those. Little patterns though, I love little patterns in mathematics. So one of the patterns that you should see here is that the derivative of the functions or the inverse trig functions that don't start with they're all positive. Well, I say positive, but they all have positive signs. Technically, the derivative of the secant inverse could be negative because you don't know what x is. But as far as signs go, SIGN signs, the derivative of the sine inverse, the tangent inverse, and the secant inverse all have positive signs in front of them. And the derivative of the co-functions, or the cosine inverse, the cosecant inverse, and the cotangent inverse, they all start with negatives. And they're the negatives of their co-functions, actually. So, that being said, let's go ahead and pick one and prove one, right? They all prove basically the same way. So, picking one and proving one doesn't really truthfully matter here. That is a little bit of a fib because the secant inverse one is a little tricky because of how we define the secant inverse in calculus. So let's start with, let's go ahead and just do the sine inverse. That's a typical one I think most people prove in class. So we'll start there. And then I will hop over to the secant inverse just to showcase that one. But we're going to prove that the derivative of the arc sine, or the sine inverse of x, is equal to 1 over the square root of 1 minus x squared. So this starts with us just saying, let y equal the sine inverse of x. Because you can't dive into the derivative of the sine inverse. You just can't take the derivative of the sine inverse if you don't know it. We're trying to prove the derivative is equal to that ratio, 1 over the square root of 1 minus x squared. But you cannot just assume that's the case. So we're going to start by saying let y equal the sine inverse, and then we're going to trade that sine inverse function, or basically manipulate this to be written in terms of sine. So if we let y equal sine inverse of x, then sine of y, by definition, should equal x, because they're inverse functions of one another. And now that we have that, I could take the derivative of sine of both sides of that equation implicitly. So this implies the derivative of sine, which is the cosine of y, times the derivative of the y that's inside that sine, should equal the derivative of x. Again, all I did was implicit differentiation. I took the derivative of sine, turned into the cosine, and wrote that of y, because that's what you have to do. And then I hopped inside the sine and took the derivative of its argument, which is derivative of y with respect to x. And on the right-hand side, I took the derivative of x here, and that ends up being 1. If I divide both sides by cosine of y, I get the following. dy dx is equal to 1 over the cosine of y. Now all we have to do is figure out what the cosine of y is. There are quite a few ways for somebody to talk about this, but honestly, the best way to talk about this is using the idea of inverses to remind you of how inverse functions work. Inverse trig functions is what I meant, and what quadrants they return into. So I'm going to, off to the right, remind you that the sine inverse of x returns angles between negative pi over 2 and positive pi over 2. That's what the sine inverse returns angles between. So sine inverse of x, it's returning y. We could see that. That's what we said. Y is equal to sine inverse of x. So our y values are between negative pi over 2 and pi over 2 as far as rotational angles. Again, if you think about that, that means your angles that you're dealing with here, y's, are going to be in quadrant 1 or quadrant 4. Sorry, I was going to say 2. My brain today is shot. All right. Remember, y is playing the role of an angle here. So now think about this. The cosine in quadrants 1 and 4, the cosine is positive. So this is where your trig prerequisite becomes massively important. Since the cosine is positive in both of those quadrants, I don't have any ambiguity when I draw a triangle here. And this is why I say I'm doing the inverse conversation first, and then we'll draw a triangle. Because if you draw a triangle right now, look what happens. We know that the sine of our angle y, and I'll just zoom in here, the sine of our angle y is opposite over hypotenuse. And it's written as x over 1. So the opposite is x, the hypotenuse is 1. And I can use the Pythagorean Theorem to find this missing side. It's going to be the square root of 1 minus x squared. I know it's real blocky, sorry about that. Or I could have written that triangle in quadrant 4. It still would have been a positive square root of 1 minus x squared. What would be disastrous is if we wrote the triangle over here. If we did that, it would be a negative square root of 1 minus x squared. But luckily, y does not return, or sorry, sine inverse of x does not return an angle in quadrants 2 or 3. It only returns in quadrants 1 and 4. So that horizontal side will always be positive. And so we know that the cosine of our angle, which is adjacent over hypotenuse, is just the square root of 1 minus x squared over 1. And that will imply that dy dx is equal to 1 over the square root of 1 minus x squared. They almost all work this way. Like I said, the secant's the oddball. But every other one does work nicely like this. Oh, and I should say, that is the end of that proof, QED. We have proven now that the derivative of y with respect to x, and y is the sine of x, sine inverse, sorry, of x. We've proven that that is equal to 1 over the square root of 1 minus x squared. Again, because y is the sine inverse. So that's the proof. That's how that works. And like I said, almost all of them work in a similar fashion. The only oddball is the secant inverse, and that is because of the fact that in calculus, the secant inverse, you're so used to saying like, well, maybe I should write this down. You're so used to knowing that the cosine inverse of an angle, or not of an angle, of a ratio, returns an angle between 0 and pi. And so most students would think, well, since secant is the reciprocal of the cosine, then secant inverse must also return an angle between 0 and pi. And you can define it that way. However, we don't in calculus for a very, very specific reason, which I'm not going to get into in this video. But it's more important to see that justification in calculus, sorry, Calc 2. But I will go ahead and just state it right here. The secant inverse, it returns an angle between 0, actually not including 0. No, actually it does include 0. From 0 to pi over 2, not including pi over 2, union, or I'll say and, an interval, an angle between pi and 3 pi over 2. In other words, the secant inverse returns in quadrants 1 and 3. It is positive in quadrant 1, the secant is, and the secant's negative in quadrant 3. So you get all bases covered here. But very critical that that's how you do this. That's how we define this in calculus. And we're going to see why, because I'm going to prove the secant one right now. So recall, we're claiming that the derivative of the secant inverse, sorry about the screen, is 1 over x times the square root of x squared minus 1. Well, we're going to start this the same way we did the other example. We're going to go ahead and let y equal the secant inverse of x. And then I'm going to note immediately that y is either in quadrant 1 or y is an element of quadrant 3. And that is again because we have defined the angle returned by the secant inverse to only return between 0 and pi over 2 and pi and 3 pi over 2. That's just critical for this proof. Well, if y is equal to secant inverse of x, then x is equal to the secant of y. And I'll go ahead and take the derivative of both sides. The derivative of x with respect to x is 1. The derivative of secant with respect to x is secant tangent. Remember, the arguments are y. And then you take the derivative of its argument y there. So it's derivative of y with respect to x. I can solve this for dy dx by dividing both sides by secant tangent. So I get 1 over the secant of y, tangent of y, is equal to dy dx. We do know one thing about secant of y. We know the secant of y is actually x. That's how we defined it. So we'll go ahead and replace that. That's 1 over x times the tangent of y equals dy dx. And finally, because it's trigonometry, I'm going to draw a triangle. Now remember, the secant inverse will return an angle in either quadrants 1 or quadrant 3. Let's draw them that way. Okay. So in quadrant 1, let's just pretend that it returned the angle in quadrant 1 just for a moment there. Well, we know that, I'm just drawing an altitude down to create a right triangle. We know that the secant is hypotenuse over adjacent. And we know secant of y is x over 1 right here. I'm waiting for the screen to clear. There we go. Secant of y is x over 1. So hypotenuse should be x and the adjacent side should be 1. Let's go ahead and write that in. Draw that in, that is. Slowly move over. So hypotenuse should be x here and the adjacent should be 1. And if that were the case, then by the Pythagorean theorem, this would be the square root of, let's see, x squared minus 1 Yeah, that's right. Okay, so what about if our angle returned into quadrant 3? I wrote a y hat in there because technically y would be a reference angle, but whatever. It's not that big of a deal. Draw an altitude in here. There we go. And you see this and you say, okay, well, let's see, the secant that we've defined is x over 1. So the hypotenuse has to be of length x, and the adjacent side has to be of length 1. And then you should say, wait, that's totally wrong, because this distance, I shouldn't say this distance, I should say this x value right here is supposed to be negative, isn't it? It is supposed to be negative. X is supposed to be negative over here. So what are you going to do? Well, a lot of people are going to think that I'm hand waving here, and I'm totally not, actually. You're going to make this negative because it is negative, but you can't leave that as negative without adjusting x, because remember, the secant of y is supposed to be x over 1, not x over negative 1. So if I wrote the secant of y right now, it would be x over negative 1 by the picture, which is a negative x, which is not what I want. So what I'm going to do is put a negative right there. And now the secant of y is actually negative x over negative 1, which is x, and it works out. Now, you should also be very aware. You should say, wait a second, but negative x is a hypotenuse length, and that hypotenuse, they can't be negative. Well, it's not, actually. You're in quadrant 3, and the secant in quadrant 3, is supposed to be a negative number. So x is actually a negative number. If x is a negative number, you had better put a minus sign in front of that x to make that hypotenuse positive. There you go. That's how that works. All right. So using the Pythagorean theorem, you get that this distance right here is a square root of negative x squared, negative x being squared, so x squared, minus a negative 1 being squared, 1. But it's going to be negative because it's a y value. It's in quadrant 3, so it's a negative value. Now, go back to what we were working on. What is the tangent of that? Tangent is opposite. Let me point at that. Opposite over adjacent. So the tangent is going to be the tangent of that y hat there, if you will. Technically, it's y now. So tangent of y will be opposite, which is negative square root of x squared minus 1, over adjacent, which is negative 1. The negatives cancel, and it again is a square root of x squared minus 1. So there you go. In either case, I didn't say it in the black ink, sorry about that, but in either case, the tangent is the square root of x squared minus 1 over 1, or square root of x squared itself. So now we can go back over here and just say that implies 1 over x times, rather than the tangent of y, square root of x squared minus 1 is equal to dy dx. QED. So we are done proving that. Now, on an exam, I have my students prove these. I don't have them prove the secant one because I've just done it and I think that's a little bit more challenging, but I can pick any of the other ones and they should be able to prove them. I don't like the cosecant either, but I like all the other ones. All the other ones are fair game for an exam. I'm saying that because my students should be watching this so that they know what I concentrate on. All that being said and finally done, we can go ahead and just do a single derivative, because really these are just a table of, you're just using a table of derivatives at this point. You do have to commit, like I said, the sine inverse derivative to your memory and the tangent inverse derivative to your memory. I require my students to memorize those because they are oh so important for Calc 2. However, the secant inverse, I don't require them to memorize, but it's within this problem. So let's find the derivative of this function. It's a product rule, right? It's a product of this and a product of that. There we go. So let's go ahead and find g prime. G prime is going to be the derivative of the first function. So I will actually write it that way, d dx of this x squared minus 1 to the 1/2. And then times secant inverse plus the first function, which is square root of x squared minus 1. Notice how I use radicals when I'm not taking derivatives, and I don't use radicals when I am taking derivatives. It's a habit of mine, I suppose. So I just wrote out the product rule, and now I'm just going to take the product, right? The derivative of something to the 1/2 is 1/2 times that something to the negative 1/2 by the chain rule, times the derivative of its interior, which is 2x, and then that's attached to a secant inverse of x, plus the square root of x squared minus 1 times the derivative of the secant inverse. It's so new to us, we should probably look at it really quickly, so I'm hopping back so you could see it. The derivative of the secant inverse is 1 over x times the square root of x squared minus 1. So 1 over x, even though we just proved it, I just had to look that up. 1 over x times the square root of x squared minus 1. Notice how beautiful this is. The square roots of x squared minus 1s cancel. And we now have, let's see, also these 2's cancel, don't they? All right. And also this negative 1/2 just parks that square root downstairs. So this is going to be an x secant inverse of x all over the square root of x squared minus 1, and then plus 1 over x. I suppose that you could get a common denominator here if you really wanted to. That would be x squared secant inverse of x plus the square root of x squared minus 1 all over x square root of x squared minus 1. If you want to combine those two fractions, you totally can. All right, there's not much else to say, because when you're dealing with inverse trigonometric functions and their derivatives, there are some applications. They usually involve a lighthouse and a rotating light and silly things like that. But for the most part, it's mostly mechanical. So I hope this was helpful. And if you have questions, ask them in the comments. I will reply, I promise.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.